Hello everyone, welcome to lecture on digital logic design. I'm Dr. Vilayat Khan. In this lecture I will talk about sequential logic and also about the basic flip-flops. Most commonly used flip-flops, D flip-flop, JK and T flip-flop. So let's begin with what is sequential logic. In digital logic design, circuits are normally designed using two different types of logics. One is combination logic and the other is a sequential logic. In combination logic, a combination circuit is designed using a set of logic gates, and it gets an input or n-bit input, and it produces an m-bit output. The output at a particular time is a function of the input provided at that particular time, and it doesn't depend on anything else, just the inputs. So this is called combination logic. Combination circuit, it gets input and it produces output at the same time, and the output is dependent only on the current input provided. If memory elements are added with this combination circuit, and these memory elements store the output that is produced at a specific time, this output, which has been stored in the memory elements, is used as a input next time when an input is given next time. Then the output that is produced is not only a function of the current input but also the output that was produced before and was stored in the memory element. So when an input is provided, it creates an output, and also a copy of that output is stored in the memory elements. Now whatever it has been produced here becomes the state of the circuit, and next time when an input is given, this input together with the current state of the circuit produces the current output. So in sequential logic, the current output not only depend on the current input but also the previous output or the current state of the circuit, which is stored here in the memory elements. Normally, flip-flops are used as memory elements to store the state of the circuit and to synchronize the operation of flip-flops. Digital signals called clock pulses are used to synchronize the operation of flip-flops. So this is sequential logic, where a combination circuits get inputs, it produces outputs, and the output is stored in the flip-flops synchronized by the clock pulses. Each time an input is given, the current state of the circuit, which is there in the flip-flops, as well as the current input produces the output. So in sequential logic, the output is not only dependent on the input but also the current state of the circuit. The most common flip-flops are discussed here. This is a very simple basic flip-flop called SR latch implemented with NOR gates. As we know the operation of NOR gate, it is very simple to understand the function of this SR latch implemented with NOR gates. We have two NOR gates, each with two inputs. One of the input is taken from the outside. The first input is reset, represented with R. The second input is set, represented with S. And the other input of each NOR gate is taken from the output of the other NOR gate. They are very simple to understand. This output is given as an input to this NOR gate, and this output is given as an input to the first NOR gate. The output of each NOR gate is called Q and the output of the other NOR gate is called Q prime. So there are two inputs of this SR latch and two outputs. The inputs are reset and set, and the outputs are Q and Q prime. Q is prime for the all valid outputs. Normally, Q, the output given here, is the complement of the output given here. So they are the complement of each other. And if they are not complement of each other, then such outputs are indeterminate or invalid outputs. So this is a simple SR latch with two inputs implemented with NOR gates and with two outputs. Now I will explain how it produces outputs when inputs are given. Now remember the operation of a NOR gate. A NOR gate gives 1 when at least one of the input is 0. And when both of the inputs are 1, it produces 0. Otherwise, it produces 1. When one of the input is 1, it produces 0. And when both of the inputs are zeros, it produces 1. Okay, so this is the function table or the truth table for this SR latch with NOR gate. It has two inputs SR and two outputs Q and Q prime. When 1, 0 is provided as the input, 1 at the S input, 0 at the R input, then the output will be 1, 0. When 0 is given here, the output is dependent on the next input. So we cannot decide what is the output here. But here, it is simple. This is 1, so we know that this is 0. Q prime is 0. This 0 is given as input here. It is now defined. 0, 0, it produces 1. When both of the input of the NOR gates are 0, it produces 1. And if at least one of the input is 1, then it produces 0. So when 1 is provided at the set input, 0 is provided at the reset, it creates 1 here and it creates 0 here. Now when 1 is given at the output Q, then this is called set state of the latch. When 0 is produced at the Q output, it is called the clear state of the flip-flop. So when we want to set flip-flop, we can provide 1 at the S input, 0 at the R output input. So this is set state. Similarly, after providing 1, 0 at the input, we get 1, 0 at the output. Now if we give 0, 0 at the input, the state will remain as it is. Now 1, 0, when we provided 1, 0, we got 1, 0 at the output. Now this 1, 0 become the current state of the flip-flop. Now when 0, 0 is provided, after the flip-flop or the latch has this state, the state remains the same. After S is equal to 1, R is equal to 0, which is here, and 0, 0 is provided, the current state or the previous output will not change, 1, 0. Now let me show you how it happens. 0, 0 is provided here. Both of the NOR gates get 0, but we cannot determine the output because of the property of the NOR gate. So we have to use the previous output, which is 1 here. This 1 is given here. This becomes 1. This becomes 0. Q prime becomes 0. This becomes 0. So two inputs of this NOR gate becomes 0, and we get 1. So 1, 0. Similarly, when 0 is provided at the S input, 1 is provided at the R input, then 1 comes here. As one of the input is 1, we will get 0 here at the Q output. And when this 0 is given here, we get 1 at the Q prime output. So Q is 0 and Q prime is 1. So what happened? When 1 is provided at the R and 0 is provided at the S, then the flip-flop resets. Resetting means the Q output is 0. So by providing this input, we reset the flip-flop. And if we again provide 0, 0 after this input, then the present state or the current state of the flip-flop is maintained. The output doesn't change. After S is equal to 0 or is equal to 1, if we provide this input, we get this. Similarly, if we provide both of the inputs as 1, 1, we get 0, 0 here because one of the input of the NOR gate is 1, we get 0 at the output. So both of the NOR gates get 1 at one input 1, so we get output 0, 0 both of the outputs. But this is an invalid state or invalid output because Q and Q prime are not the complement of each other. If they are not the complement of each other, then that state or that output is invalid or forbidden. Okay, so when we provided 0, 0, it gave us 1, 0, but when later on we provided 0, 0, we got 0, 1 instead of 1, 0. The reason is that SR latch implemented with NOR gate and the other latches as well the output is not only dependent on the current input but also the previous output. We got 1, 0 when 0, 0 was provided because of the current state was 1, 0, but later on when 0, 0 was given, we got 0, 1 because the current state was 0, 1. The current state changes, the input produces different output because the output is not only dependent on the current input but also the current state or the previous output of the latch. This is another simple SR latch implemented with NAND gate. In the previous latch we had NOR gates, but here we have NAND gate. Now in this latch we are having NAND gate, and we know that in NAND gate when both of the inputs are 1, we get 0, and when one of the input is 0, we get 1. That is the function of a NAND gate. Now if we keep that functionality of the NAND gate in our mind, it is very simple to understand the operation of this SR latch implemented with NAND gate. Here is the function table of the NAND gate, SR latch with NAND gate. When 1, 0 is provided at the input, 1 is provided at the S input, 0 is provided at R. This 1 comes here, but we cannot predict the output here. But here, when 0 comes here, we can say that the output is 1 because one of the input is 0. The AND part of the NAND gate will give 0 and the inverter will make it 1. So we got 1 here, Q prime is 1. This 1 is given as input to the first NAND gate. We got 2 inputs of this NAND gate as 1. We get 0 here. So Q is 0. So when in the NAND gate implementation, when 0 is provided at the R input, it resets the flip-flop. While in the NOR implementation, when 1 is provided at the R input, it resets the flip-flop. But here, you can reset the flip-flop with 0 at the R input. Similarly, if we provide 1, 1 at both of the inputs, the current state of the flip-flop is maintained, just like in the NOR implementation, 0, 0 would maintain the current state of the flip-flop. So it's the opposite now. 1, 1 will keep the current state of the flip-flop. So after S is equal to 1, R is equal to 0, which is here, when we provide 1, 1, we get the same output as was before or as was for the previous input. When the input is 0, 1, 0 is here, 1 is here, so it will set the flip-flop. How? 0 is provided here, we got 0, one of the input is 0, so we get 1 here. So Q is 1, which is here. This one is given as input to the second NAND gate. Both of the inputs are 1 now. We get 0 here. So Q prime is 0. Now getting 1 at the Q input output is called set state of the flip-flop. So by providing 0 at this input, we set the flip-flop. And now while the flip-flop is currently set, if we give 1 1 as the input, it will remain as set. It will not change the current state of the flip-flop. So after S is equal to 0, R is equal to 1, which is different than this. When 1 1 is provided, we get 1 0 at the output. So again, just like NOR gate implementation, when 1 1 is provided, we get 0 1. But later on, when 1 1 is provided, we get 1 0. Why? Because of the previous input. The previous input here is different than the previous input here. So the current output not only dependent on the current input, but also on the previous input as well, or the current state of the latch. Similarly, when we provide 0 0, one of the input of the NAND gate is 0, so we get 1 1 here. And this 1 1 is invalid or forbidden state due to the fact that Q and Q prime are not the complement of each other. So such an output is called forbidden. Now clocked ORS latch with NAND. On previous slide, we had this ORS basic latch implemented with NAND gate. If you want to control the operation of this basic latch using a clock pulse or an enable input, this is normally the clock pulse, then we can do that by connecting an additional NAND gate with the S input and an additional NAND gate with the R input and providing this clock pulse to both of these NAND gates. Now this is the clocked ORS latch, and this enable or the clock pulse simply control the operation of this flip-flop or the pressure or the inputs. So whenever the enable is 0, regardless of the input, whenever the enable or the clock pulse is 0, regardless of the inputs S and R, the current state of the flip-flop will not change. When enable or the clock pulse is 1 and we change the S or inputs, we will get the same result as was for the basic ORS latch with NAND gate, or you can say the same operation, we will get the same result as we had for this part of the latch. However, let me explain. When 1 is given here, we get one of the inputs of these two NAND gates as 1. So then outputs of these NAND gates depend on the other inputs. So when 0 0 is given here, we get 1. 0 0 is given here, we get 1 and 1 here. As we saw in the previous slides, when 1 1 is given, the current state of the flip-flop is maintained. So when 0 0 is given here, we get 1 1 here, and for the 1 1, no change, or the flip-flop, the current state of the flip-flop is maintained. Similarly, when 0 1 is provided here, 0 1. So 0, it will make this S as 1, and this is 1, so it will make this input 0. So by providing 0 at the R input, will reset the flip-flop. Reset the flip-flop. Here it becomes 0, and that is a reset state. Similarly, 1 0. 1 0. When 1 is provided here, we get 0 here. And when 0 is provided here, we get 1 here. So 0 at the S input will set the flip-flop. Set the flip-flop. That means Q will become 1. Similarly, when 1 1 is provided here, we get 0 0 here. By providing 0 0 here, 0 0, we will get, when 0 0 is given here, we will get 1 1 here, which is an invalid state or indeterminate state. So this is a clocked ORS latch with NAND gate. This is an ORS latch with NAND, but it is clocked or controlled by a clock pulse or an enable. So you can, whenever you want to change the state of the flip-flop, just provide the clock pulse and give a particular input and it will change the state of the flip-flop. D flip-flop, when in the clocked RS flip-flop and D flip-flop are quite similar. This input is inverted and given here. There is a single input D, which is now called D, but this single input, which was S in the clocked RS flip-flop with NAND gates, now we call this input as D. This D is provided directly to this NAND gate, but it is inverted to be given to the second NAND gate. So it's inverted here. The operation of the rest of the flip-flop is exactly the same as it was before, but let me explain how it will operate. When D is a single input and we have the present state of the flip-flop which was produced before, or the previous output, and we want to get output for the current input, and that output is called next state of the queue or next state of the flip-flop. So let me start with the truth table. To understand that, we can compare the values here with the function table which is given here for this basic flip-flop implemented with NAND gate. When we give input here, whatever the outputs are produced here, this basic flip-flop will operate as it was before, and which is described here in this function table. So let's begin. When 0, D input is 0. 0 is provided here. Obviously, we get 1 here. When 0 is provided here, this NAND will make it 1, and when both of the inputs are 1, we get 0 here. So when 0 is provided here, we get 1, 0, 1, 0. 1, 0 is provided, so it will reset the flip-flop. That means Q is 0. Next state of Q is 0. We do not mention Q prime because now we know that it is the opposite of Q, so it's not important to mention it. Otherwise, it can be mentioned here by just like we did it here. Okay, so when 0 is provided, it will make the S here as 1, and it will make the R here as 0. So 1, 0. So 1, 0 will reset the flip-flop which is here. So the flip-flop is already reset, but when you provide 0, it will reset the flip-flop. Okay, so when the current state is 0 and the input at the D here is 1, it will make S as 0 and R as 1. Now, when we provide 0 at the S input in the basic latch with NAND gate, it will reset. It will set the flip-flop. By setting the flip-flop means we get 1 at the Q output, which is here. Or you can also look the same result here. S is 0, R is 1. So for the SR, 0, 1 is the input, 0, 1 is the input, so it will set the flip-flop. We get 1 for the Q and 0 for the Q prime, which is here. So for the Q, we get 1. So it will set the flip-flop. Similarly, when we give 0 at the D input, we get 0 here. By providing 0 here, we will get 1, 0 here. So at the SR input, we get 1, 0. Look here, 1, 0. So it will reset the flip-flop. Even if it is set before, but it will reset the flip-flop. By resetting, we mean Q becomes 0. Similarly, when 1 is provided at the D input, 1 is provided here, it will make the S and R inputs of the basic latch as 0 and 1. So look, 0 and 1 here, 0 and 1. So it will 0 at the S input means setting the input, setting the flip-flop. Setting means we get 1 at the Q output. We get 1 at the Q output, which is here. So we got all the possible combinations for the D and the current state of the flip-flop. So when we want to set the flip-flop, we give 1 here. When we want to reset the flip-flop, we give 0 here. By 0 input, we reset the flip-flop or clear the flip-flop. By giving 1, we set the flip-flop. Here is the K-map for this table. These are the outputs. So minterm 0 is 0, minterm 1, yes, minterm 2 and minterm 3. So we got 2 squares with 1. By simplifying it, we get a single 2 square group. So the next state of Q, or which is also represented with Qt plus 1, is equal to D. That is a simplified Boolean equation for the next state of Q, and which is also clear here. So whatever you give at the D input, that becomes the state of the flip-flop. I repeat, Qt plus 1 says the next state is equal to the D input. So in the D flip-flop, whatever you give at the D input, that becomes the state of the flip-flop. Here is the graphical symbol for D flip-flop. You have 2 outputs, Q and Q prime, and a single input. One is clock pulse and there is a single input D. So when you give 0 here, we get 0 here. When you give 1 here, we get 1 here. So if you want to change or store a bit on this flip-flop, just provide the bit here. 0, we get 0. 1, we get 1. Now we have clocked OR sledge with NOR gate. Previously we had clocked OR sledge with NAND gate. It's the same OR sledge implemented with NOR gate, but it has been clocked using these 2 AND gates and a clock pulse. Now the rest of the operation is the same, but now we can control the operation of this whole flip-flop using this clock pulse. Now to see the outputs for all possible input combination while having the current state of the flip-flop, we have 3 inputs, the current state of the flip-flop, and 2 inputs, S and R, and we are interested to find the next state of the flip-flop, which is Q, T plus 1. So if Q is the current state, the next state is represented with Q, T plus 1. Okay, so for the first, when we provide 0, 0 here, 0 is provided here, 0 is provided here. So assuming CP is 1 all the time, we get 0, 0 here. So when we get 0 and 0 for both of the RSLH inputs, the current state of the flip-flop will remain, and as the current state is 0, it will remain as it is. When we provide 0, 0, the current state doesn't change. In the RSLH implemented with NAND gate, when we provide 1, 1, the current state doesn't change. But here it is the opposite. When we provide 0, 0, the current state of the flip-flop doesn't change. So the current state of the flip-flop is 0. It does not change. It remains the same. The current state is 0, but we want to reset. It is already reset, so when we want to reset, it will remain as reset. The current state is 0, and we want to set it because S is 1 or is 0, so we want to set it. So we will get 1 here. Let me explain this input combination, how we get 1. So we provide 1 here, and we provide 0 here, assuming CP is 1. So we provide 0 at the R input, so we get 0 here, and we get 1 here. 0, 1. as we have NOR gates here. So when we get 1 here, we get 0 at the Q prime. This 0 is given as input here. We got 2 of the inputs, 0, 0, so we get 1 here. So Q becomes 1. Similarly for other inputs. So when 0 is the current state and we provide 1, 1, we get indeterminate state or invalid state. Similarly, when the flip-flop is set and we want to give 0, 0 at the input, the current state will remain, which the current state is 1, which is set, so it will remain as set. So 0, 0 doesn't change the current state. 1, 1 is indeterminate. For all other two combinations, it becomes set or reset. So here it is already set and we want to reset it. So it will change from set to reset state. That becomes 0. Similarly, it is set and we want to set it. So it will not change because it is already set and you want to make it set. So it will remain set. It is set, but we want to give 1, 1. So 1, 1 input combination is an invalid input combination because we get both of the outputs Q and Q prime same. When we get 0, 0 or 1, 1 at the outputs, this output is indeterminate. Okay, so assuming indeterminate or the don't care, it can be 0 or it can be 1, so we consider them as don't care condition. Here is the map, 3 variable Boolean map, the K map. Okay, so the indeterminate state are represented with X, which are don't care condition. So when we group them, we get a 4 square group and also a group of 2 squares. The product term for this group is S and the Boolean variable, the function is Qt plus 1. So Qt plus 1 is equal to S for this group, and for this group we get Q and R prime or R prime Q. So S plus R prime Q is the Boolean equation for the next state. But here we must say that we shall not provide an input where both of the inputs are 1, 1. Look here, the indeterminate state, 1, 1 is the input, 1, 1 is the input. In other words, we must provide at least 1, 0 at the inputs. We can provide 0, 0, we can provide 0, 1, we can provide 1, 0, but we cannot provide 1, 1 at the input. To logically say that, we write S and R is equal to 0. We say that SR must be equal to 0. That means if SR can only be 1 when S is 1 and R is 1, then we get 1, and that is not allowed. SR must not be equal to 1. That means SR is always equal to 0, and logically that means one of the input in S and R must be 0. Now in this clocked OR sledge implemented with NOR gate, we want to remove these indeterminate state. We want to avoid them, and we can avoid them if we feed this output Q with the first AND gate and this output Q prime to the second AND gate like this. This output is fed back to the first AND gate and this Q prime output is fed back to the second AND gate. The rest of the flip-flop is the same ORS flip-flop, clocked ORS flip-flop implemented with NOR gate, but now these letters R and S are called J and K. So this becomes JK flip-flop. The rest of the flip-flop is exactly the same as ORS, clocked ORS flip-flop implemented with NOR gate. But these letters S and R are now called J and K, and this is the same clock pulse input. So this becomes JK flip-flop. Now the rest of the operation of the JK flip-flop is exactly the same as clocked ORS flip-flop, but these input combinations are different. The outputs for these input combinations are different. They were indeterminate in the RS clocked flip-flop, but they are now determined. How? Let me show you. When 1 is provided at the JK input, 1 is provided here, 1 is provided here, and we have the current state is 0, the previous output or the current state is 0 here. So when all of the inputs of these gates are 1 except this input, which is 0, because current state is Q is 0, so this input is 0 and all other of the inputs are 1, we get 0 here and we get 1 here. So when R is 0 and S is 1, it will set the flip-flop. That means we get 1 at the output. Similarly, so we have now defined, instead of indeterminate, now we know what would be the output, that is 1. Similarly, when 1 is provided at the JK input, but the current state is 1, then we get all of the inputs of these AND gates as 1 except the Q prime, the output, the feedback from the Q prime is 0. So this input to the second AND gate is 0 because Q is 1, so Q prime must be 0. So this is 0. When this is 0, we get 0 at the S input and we get 1 at the R input. So it will reset the flip-flop. By resetting we mean it will generate 0 at the Q output. So now in the RS flip-flop implemented with NOR gate, we had indeterminate for the 1 input, but now we have 0. In other words, whenever in the JK flip-flop, whenever 1 is provided at the input, it will complement the current state of the flip-flop. When 1 is provided here, if the current state is 0, it will complement it to 1. If the current state is 1, it will complement it to 0. And the rest of the operation are exactly the same for RS flip-flop, clocked RS flip-flop implemented with NOR gate. So in the JK flip-flop, by using these feedback lines, we can avoid the indeterminate state. Now everything is defined. Although the outputs are defined for all the input combination. This is a truth table. In the clocked RS flip-flop, we had X here, we had X here, but now we know that it is 1 here and we know that it is 0 here. So by grouping, we now have the same two groups, but this group is not a 4 square group, but it is a 2 square group. So we have the Boolean equation Qt plus 1 is equal to JQ prime plus K prime Q. What are the major differences? Remember that instead of RS we now have JK. Instead of RS we now have JK. I have kept these letter R and S just for comparing. So we got the Boolean equation JK Q prime plus K prime Q. It is a graphical symbol. Again, instead of RS we have JK letters inside the graphical symbol. Now this is JK flip-flop where we have NOR gates. This flip-flop can be converted into a T flip-flop by combining these two JK inputs and renaming it with T, like this. What we did, here we had the J input, here we had the K input. We just combine them into a single input and we just connect them together and it becomes a single input and we label it as T. Now when we provide a 0 here, we get 0 0 at both of the JK inputs which is on the previous slides. So the rest of operation is exactly the same. But now as we have a single input, we have a single input here. So with the current state Q, we can determine the next state, when the input is provided, the input T is provided. For example, the current state is Q0 and T is 0, so it will make these two inputs 0. It will make these two inputs 0 and the current state is 0. So 0 is here, 0 is here, and we get 0, 0 here. Regardless of these lengths, we know that one of the input is 0, so we get 0, 0 here. And we know that when 0, 0 is provided to the basic latch, RS latch implemented with NOR gate, it will maintain the current state. So the current state is 0, so it will maintain it. Now for 1, 1, for when T is equal to 1, we get 1 here, we get 1 here, and the clock pulse is 1. But Q is 0, so Q is 0, so we will get 0 here and we will get 1 here. 0, 1. What we get? I repeat, T is 1, so we get this input 1, we get this input 1, and the clock pulse is already 1. But the current state is Q, which is 0. 0 is provided here. We get 0 here and we get 1 here because Q prime is 1. We get 1 here, we get 0 here. So it will, as we have 1 at the OR input, here is 1 at the S input, here we have S, here we have OR. We get 1 here, we get 0 here. So when we get 1 at the S input of the basic RS latch with NOR, it will set the flip-flop. By setting we mean it will give 1 at the Q output. Now when the current state is 1 and we give 0 at the T input, so we get 0, 0 here, and by 0, 0 we mean it will maintain the current state. So the current state is 1, it will remain 1. When the current state is 1 and we provide 1 here, we provide 1 here, so we get 1, 1 here, but Q is equal to 1, so it will 1, so all the inputs of this AND gate are 1, so we get 1 here, but we get 0 here. Why? Because Q prime is 0, so we get 0 here. So 0 at the S input, 1 at the R input will reset the flip-flop, and it is preset. So this is the truth table for the T flip-flop, and this is the graphical symbol for the T flip-flop. Here we have the K-map for this function Qt plus 1, and it is Qt plus 1 is equal to TQ prime. We have two groups, TQ prime plus T prime Q. This is the Boolean equation for the next state of the T flip-flop. But here we can see that when T is 0, it will keep the state. When T is 0, it will keep the state. Current state is 0 and we give 0, so it will keep the state. Current state is 1 and we give 0, it will keep the state. But by providing 1 at the T input, it will toggle or complement the current state. When we provide 1 here and the current state is 0, it will toggle it, it will complement it. We get 1 here. When we provide 1 at the T input, but the current state is 1, it will toggle or complement the current state, 0. So in the T flip-flop, we have 1 input, and this 1 input toggles the current state of the flip-flop. If the current state is set state, it will reset by providing 1. If the current is reset and we provide 1 at the T input, it will set it. And by providing 0, it will just keep the current state. And by providing 1, it will toggle the current state.